All right, let's go through the test real quick. An example of a constant pressure process. Actually, none of those above are constant pressure process. The pressure changes through all of them. The use of the equation um, PV equals a constant means numerical results for compression or expansion process will be, well, they won't decrease, that's not constant. They won't increase, that's not constant. They won't change, that's not constant. Will be the same at any point in the process. That's the only one of those answers that matches the requirement for constant. A gas at 1,000 kilopascals gauge pressure and 30 degrees C is transferred from a cylindrical vessel of 1.5 meters and 3 meters long to another vessel 2.5 meters in diameter and 5 meters long. If the new gauge pressure is 150 kPa, calculate the new temperature. Well, this one's going to require P. Here we go. This one's going to require. Yep. Okay. P1 V1 T2 equals P2 V2 T1, and in this case, we're trying to find T. New gauge pressure. So we're trying to find D2. So that means that T2 equals P2 V2 T1 over P1 V1. The volume pi d squared over 4 times length for the two cylinders. And when you do that calculation, you should get 46 degrees C as your answer to that one. If compression or expansion occurs with no change in temperature, right? Change in temperature, that's the definition of an isothermal process. So no change in temperature, isothermal it is. The formula for work P1 V1 minus P2 V2 over N minus 1. We can't use that for an isothermal process, N equals 1, so that doesn't work. We could use it for an isentropic process, we could use it for an adiabatic process, but the most correct answer is the polytropic process is the one that we would use that for. All right. If 0.25 meters cubed of a gas at 4,000 kPa gauge pressure is expanded until the gauge pressure is 500 kPa, expansion is polytropic with N equals 1.35. Find the final volume of the gas. Well, this one is P1 V1 to the N equals P2 V2 to the N, or V2 is equal to P1 V1 to the N over P2, and then all to the 1 over N. And so that allows us to strip that off to get the value of actually V2. We get 1.04 as the answer to that one. Compression requires that work be done not by the gas, that's expansion, work be done on the gas, that's compression. The pressure volume curve for adiabatic expansion, we talked about this in class, and if we're going from expansion, we're going from a small volume to a large volume, from a high pressure to a low pressure, so 1, 1, 2, 2, and we're doing this. Well, the isothermal will end up with the highest pressure because we have to add heat energy, and the adiabatic will wind up with the steepest curve of everything else will be the quasi-adiabatic in between those two. Absolute pressure can be defined as the sum of the gauge pressure reading plus the atmospheric pressure. And question number 10. Yep. What mass of air can be held in a storage cylinder? That? Well, PV equals MRT. M equals PV over RT. Make sure we get this This is absolute, so we don't have to change that. So that's 1500. Volume is 9.5, 0.287, and 95 plus 273. Everything has to be absolute. It's a perfect gas calculation. So we do that, we get 134.9 kilograms. 10.4 cubic meters of air is compressed at constant temperature to 5.1 meters cubed and 750 kPa gauge. Calculate the magnitude of the work done. Well, we can't use the P1 V1 minus P2 V2, so this is the PV times the ln of V2 over V1. And we can use either PV we want, so this can be 5.1 times 850, that is gauge, right? And then times the ln, and it's V2 over V1, which is going to be 5.1 over 10.4, and the answer is going to be minus 3089. Minus, because this natural logarithm comes out minus, we're compressing it, work's going in. Work in is minus, that's the definition. A gas expands adiabatically. That really, the adiabatic doesn't matter, just tells us that we can use P1 V1 minus P2 V2 over n minus 1. And so what we get is, because we've got absolutes in here, we're looking good. We don't have to do anything changing there. So we've got 1025 times 1.5 minus 225 times 4.05, and n being 1.42, 1 minus that is 0.42 in the bottom, and we do that all, we get 1491, and that looks like that answer right there. 13, a tank contains 2 cubic feet of air, and that, by the way, is constant. We don't have to worry about that. And so 500 is going to be 514.7. 60 is going to be 520 Rankine. Temperatures increase to 150. That's going to be 710, I think. 460 plus 150, 710. 610. Right. Determine the new gauge pressure in the tank. So we can actually do that one by P1 V1 T2 equals P2 V2 T1, and since the volumes are both the same, they're gone. They'll cancel out anyway, and so new pressure. So I'm looking for P2 equals P1 T2 over T1, and I can plug all those numbers in. 514.7 times 520 all over 610, and that equals 438.8, but I still have to subtract 14.7, and that gives me 424 as my gauge pressure. Calculate the mass of carbon dioxide containing a volume of 0.09 cubic meters. Okay, this is going to be M equals PV over RT is going to be 20700. It has to be absolute. That's gauge pressure, so we have to add 100 kilopascals times 0.09, and R is going to be 0.195. We get R from C sub P minus C sub V in the academic supplement for carbon dioxide, and my temperature is 225 plus 273, and that whole thing comes out to 19.2. If you got 19.09, I'm assuming you did not add the 100 to the 20,700. Okay. Calculate the mass of carbon dioxide contained in a volume. Well, since these questions on a normal test would have wound up sequential, and I could have just asked about now the previous gas, but because the question showed up random on your online test, I had to give you the information all over again. So if I do this, calculate the mass of carbon dioxide contained in a volume of 0.09, if the pressure is that, and the temperature is that, if the gas in question is then expanded to a volume of that, in a process where P1 or PV to the 1.18 is a constant, calculate the new temperature. Well, we've got the new temperature here. We've got our new temperature is going to be T1 over T2 equals V2 over V1 to the n minus 1. We actually don't have to calculate the mass. It just happened to be in there so I could give you all the rest of the information that you needed. So T1 over T2, and so we are looking for T2, which if we do the algebra is T1 over V2 over V1 to the n minus 1, and we get 225 plus 273 over 0.25 over 0.09, and this is 0.18 there, and we get 414.3 Kelvin. So there it is right there. That just so happens that 414.3 Kelvin is 141.3 degrees C. Doesn't matter whether we have that or not. We can do it either way down here, because now we want delta U, and delta U equals mCV delta T, and delta U is 19.2 times 0.630. Again, we get CV from the academic supplement, and we have the two temperatures, 141.3 minus 225, and that comes out to minus 10, 11.4 minus 10, 11.4 is the answer for the work done.